Hello! In this video, we're going to discuss the variation theory approximation and apply it to the two-electron configuration of the helium atom. Now, you may recall that because the helium atom has 2 electrons, we cannot solve the Schrodinger equation exactly and must apply approximation methods to get solutions for the wave function corresponding to the helium atom and the corresponding energies. So we're starting with an approximation method where we're assuming orbitals, and that means that we're going to be starting with the atomic orbitals that were solutions to the Schrodinger equation for the 1-electron system, for the hydrogen atom, and for hydrogenic atoms which have only 1 electron. And we're going to assume then that the ground state electron configuration of helium has 2 electrons and both occupy the 1s orbital. The total wave function then, it corresponds to this situation here, where it's a product of a 1s orbital for electron 1 and a 1s orbital for electron 2. So that's our total wave function for the 1s2 electron configuration. So we're starting with that assumption. Now, in variation theory, we start with a trial function, essentially an educated guess as to a wave function that could be applied to the system. And again, so this 1s2 electron configuration is our trial wave function that we're going to use as our starting point. The idea of variation theory is that we're going to take this wave function and we're going to tweak it with variable parameters. And that is, there are going to be elements of this wave function that we're going to adjust and modify to yield a minimum energy configuration. So we'll take our wave function with these variable parameters, we'll plug it into the Schrodinger equation, and we'll get a solution from that, which we will then optimize to generate a minimum energy situation. And again, the concept here is that nature always moves to the minimum energy. So the wave function that we might generate, the approximate wave function that we would generate, the lower the energy of that approximate wave function, the closer it is to the real wave function. So that's the basic concept here. All right, so for 2-electron systems, if we start with this idea of a 1s2 electron configuration, here's our trial wave function, and here is the general equation that we're going to use as our trial wave function. Now, if you go back and take a look at the wave function for the 1s orbital in hydrogen, or for a hydrogenic system, we're going to note that this looks very much like that wave function. And again, here we have the product of 2 1s orbital wave functions, and that's why we have here in the exponent R1 plus R2. R1 would correspond to the coordinates of electron 1, R2 corresponds to the coordinates of electron 2. So this would be our trial wave function that we're going to start with for the 1s2 electron configuration. So what's our variable parameter? That is, what element of this equation are we going to allow to vary to find a minimum energy situation? So what we're going to do is we're going to take, if we go back and look at the 1s orbital wave functions, we had the atomic number Z for the nucleus of the corresponding system in the wave function that we see in these positions here. So we had the Z, atomic number Z in the exponent, we had atomic number Z in the coefficient multiplicative factor outside the exponent. And what we're going to do is we're changing that from Z, which of course would be 2 for the helium atom, to Z, what we call Z effective. All right, so that's the EFF subscript here. And what we're going to do is we're going to solve the equation with Z effective in the equation. All right, and then once we have the solutions, we're going to find the value of Z effective that gives the lowest possible energy. Okay, so we take this wave function and we plug it into the Schrodinger equation, and when we solve it, we get this equation here for the energy in terms of Z effective and actually the real atomic number Z. So this Z here without the subscript is actually the atomic number, which again for helium would be 2. But we can use this solution for any 2-electron system. So we could use it for lithium plus, for example. So here we have this expression, which is a relatively simple expression for energy, which depends only on the atomic number and this effective atomic number that we have here. This is actually a simplified version of the equation because it's using energy in what are called atomic units, or actually Hartrees. So in this situation, it's important to note that the Hartree is equal to 27.21 electron volts. So we'll come back to that later after we get our solutions so that we're able to compare the energy we get through this approximation method to the real experimental energy of neutral helium. All right, so here's our variational energy with our parameter Z effective. So what we're trying to do, remember, is find the value of Z effective that gives us the lowest possible energy, because the lowest possible energy is going to correspond to the situation which is closest to the real system. So how do we find that energy minimum? Well, you may recall, if you've got a mathematical function, all right, and you want to find a minimum for that function, or a maximum for that matter, for that function, we take a look at derivatives. Because at the minima and the maxima, the derivative is equal to 0. All right? So that's the key factor here. The derivative is equal to 0. So if we take our energy equation here and take the derivative of this equation and set it equal to 0, then solve for Z effective, that's going to give us a value of Z effective that would correspond to a minimum or a maximum, again, for that matter, that we can use. So we can do this in Wolfram. And actually what I've done here is, rather than using Z effective, I've replaced the Z effective in this equation with X. So if we look at this, we're taking the derivative with respect to X of X squared, and again X is equal to Z effective, all right, minus 2 times Z, the actual atomic number, times Z effective, plus 5/8 times Z effective. So we're going to take the derivative, and again we can use Wolfram alpha or the Wolfram cloud. This is how we would type it into either one of those venues to do that calculation. And again, the reason I used X here rather than Z effective in this equation was, number one, to simplify entry, and it also seems that when I experimented with this, that the Wolfram cloud or the Wolfram alpha had a more difficult time in interpreting what I meant by Z effective in this equation. So I've just, keep in mind here that I've just replaced Z effective with X. So I take the derivative, and this is what I get. It's a relatively simple one. It's certainly one that you could probably have done easily by hand, but this is how we would do it in the Wolfram universe. And so we have our result. Now again, what we want to do is find the value of Z effective, which again, remember, is X. We're going to find the value of Z effective, which gives us the lowest possible energy. So we're going to set that quantity, right here, equal to 0, and we're going to tell Wolfram to solve for X. And again, this is not a terribly difficult one to solve by hand. You could certainly do that. So we can set it equal to 0, solve for X, and we find that X is equal to Z, the atomic number Z, minus 5/16. Okay? All right, so let's take a look at helium. Helium has atomic number of 2, all right? So that means that Z effective is equal to 2 minus 5/16. So here's our value of Z effective for helium, all right? And again, remember, the idea here is that by taking the derivative and setting it equal to 0, the value of Z effective should yield a minimum energy, and that's what we're striving for, because variation theory says that the lower the energy, the closer you will be to the real system, the real energy and the real wave function. So we're going to take a look at that. All right, so what is the energy? So what I'm going to do is just take that value of Z effective, all right, and I'm going to plug it back into our energy equation, which is just simply this equation here. So I'm just taking the value that we got, plug it into that equation, all right, and this is what we get fractional in fractional form. Now remember, this is in atomic units, and so if we want the value in electron volts, we need to take that number, all right, and multiply by the conversion factor of 27.21 electron volts. So we get negative 77.4847 electron volts through this calculation. Now, you'll remember in the previous video we talked about the first approximation method that we used was to ignore repulsion. And in that first approximation method, when we just completely ignored electron repulsion, we got a value of negative 108.8 electron volts. Now, the actual value, experimental value for the energy is negative 79, so clearly the negative 77.48 that we calculated here is much closer to the real experimental energy than was the case for ignoring repulsion. And of course that shouldn't make sense. I mean, the reality is that ignoring repulsion is a very, very, very bad approximation method. The repulsion energy, the positive repulsion energy, has a significant impact on the overall energy of the system. So this method's not bad, because in fact it's a relatively straightforward approximation that we've done here with only a single parameter that we're varying, and we get within 2%, less than 2%. If we take a look at the difference here, we have less than 2% difference between this calculated value and the real value. And of course we can do additional tweaks by modifying additional parameters to get even closer than this. But this is about as simple as you can get for an approximation method that doesn't yield a very bad value at all. All right, so what does it mean? So the one question we might ask, of course, is why is this Z effective that we're using here less than Z? Well, the Z effective, remember the whole problem with the solution to the equation and finding an exact solution was electron repulsion. And so what we're doing here is we're replacing Z in our wave function with the Z effective. And by replacing the Z with the Z effective, what we're saying is that this is somehow going to compensate for this electron repulsion. So Z effective is less than Z simply because electron repulsion tends to mitigate the attractive interaction, the attraction of the electron from the nucleus. As the electrons are repelling each other, then it kind of compensates for that. So the fact that Z effective is less than Z simply indicates that electrons are repelling each other and the effect of nuclear attraction is reduced as a result. This is sometimes referred to as shielding. I really don't like that term because it is misleading in terms of the process. When you say shielding, you think about something like Star Trek, and we've got shields being thrown up all over the place, and it's blocking the electron, it's blocking the attraction of the nucleus. And that's not what's happening. Is that the nucleus is attracting with the full atomic number Z, but electron repulsion is preventing the electrons from actually perhaps getting as close to the nucleus as we might suspect, because they would get closer to each other and repel each other more. And so that's what it is. The Z effective is less than Z because repulsion compensates for nuclear attraction. And as far as the wave function goes, and we may look at the orbital wave function later on how this varies, but because Z effective is less than Z, that would mean on average, because it's lessening the effect of nuclear attraction, the orbital itself is going to be a little bit spread out more, and the average distance of the electron from the nucleus would be greater than it might be for a single electron system. So this is the first and simplest approximation that we will use, that we're introducing to deal with multi-electron systems, and it's works pretty well within this limited sample here in calculating the energy of the helium atom. And as I mentioned earlier, there are clearly far more sophisticated methods that are used to do these calculations. But this is a good first start. We'll end our video here, and we'll move on later to some additional videos on multi-electron systems.